This is CHEM100, and since there's nobody here in person to take today's exam, I assume that everyone is going to take the exam in Brightspace. So we're gonna pick up with materials for exam 4. Particularly chapter 6. But first I want to show you the material that I would hand you out in person in class is also available in Brightspace. And this is what we're going to work from for exam 4. We're going to cover chapter 6 and chapter 7. Right, so here are the PowerPoints for chapter 6. PowerPoints for chapter 7. Like I said, these are all in Brightspace, so these are the things you need to be looking for in this particular module. Well, the modules are named for the exam, so it'd be module 4. Also look for this one. This helpful hints, balancing chemical equations. Get a copy of that. And then in chapter 7, we'll get into some material here. And it'll look like that. This is the solubility chart. It won't mean anything to you now until we get into chapter 7, but be on the lookout. And then for practice, I have exam 4 review in this format, which is like an exam. And then, of course, there are also practice tests on chapter 6 and 7 in Brightspace if you want to do it that way. But if you use the paper copy I just showed you, and you have trouble figuring out why you get one wrong, when you answer the questions and then check the key, it's also in Brightspace, and you can't figure out why you're getting it wrong, then you can go to this worked problems, and it'll show you how I work the problems at least one way. There's usually more than one way to solve a problem, but when I created the document, that's the way I solved the problem. All right. So let's get my marker. So put it back in my pocket. Let's talk about chemical reactions. Up to this point in the course, we've learned the alphabet for chemistry, which is equal to element symbols. Right? And then we learned how to name compounds and write them, which is words. We created words. These are the compound formulas. And the names. How to name those compounds. Now we're going to build sentences. And these are reaction equations. They come in a specific format, and we're going to learn how to balance them so that they obey all the chemical and physical laws that we know at this point. All right, so we'll get to chapter 7 for the next lecture. Today we're just chapter 6, chemical reactions. All right, just 3 topics in this chapter. They're very important. They need to be mastered. All right, when we have a chemical reaction, we think we we see a chemical reaction. What is the evidence for the chemical reaction? Remember what happens during a chemical change. What's required for a chemical change? That is, substances change their identities. So when you start off with two gases like hydrogen and oxygen, put them together and hit them with a little spark to make them react, then what do you get? Well, you get water. Hydrogen and oxygen are elements and they're gases. Water at room temperature and pressure is a different substance with different properties, and it's a liquid. So the identity has changed. The chemical equation identifies participants in that reaction and the products of the reaction. But there's always evidence that a reaction has occurred. And it manifests itself by various signals. Some of them are visual, some of them are audible, some of them are oral. If you taste, then that's not a good thing. We don't taste things in the chemistry lab. But sometimes a product can drift toward your face and you breathe it in and you taste it on your tongue. That's a possibility. It may not be a good thing, but it happens. And those other indicators are there because we have more than one sense. We have visual sense, but maybe the reaction doesn't show any visual signs. In fact, there's some reactions that occur in such a way that we cannot sense them. We need instrumentation to sense them. Maybe they don't produce any visual or audible or olfactory signals, but they produce other signals. But many reactions do give us clues. One of those is color change. Another is the formation of a solid from a liquid. If we put two liquids together, sometimes a solid will form and drop out and sink to the bottom. We call that precipitation. Sometimes a gas is formed and you see bubbles. Sometimes you can sense heat or you can sense cold. A temperature change is an indicator, not always of a chemical reaction, but it's a clue. And if you see a flame, then it's a pretty good bet that a chemical reaction is occurring. Right? I can think of an example where there is no chemical reaction with a flame, but it's not the typical flame that you see from, say, a burning paper or wood or coal. But these are indicators of a chemical reaction. Here's an indicator. That's the formation of a gas. So what's happening here? Well, this 9-volt battery is dropped into a beaker of water, which has just a little bit of acid added to it. Remember, water is an insulator, an electrical insulator in particular, so that if you try to pass a charge through it to complete a circuit and light a light bulb, it won't work. But if you put a little acid in there, then you have a conductor. Remember, you need mobile ions in a substance to conduct a charge. So I assume that this water has in it a little bit of acid to give it allow the current to pass from one electrode to the other. And at one electrode, And I believe this is the positive electrode is on the left, and that's where the oxygen is evolved. And the negative electrode is on the right, and that's where the hydrogen is evolved. What's happening here is water, one substance, is changing its identity into two other substances, two gases. It's just the opposite of the example I gave you earlier, where oxygen and hydrogen react and give you water. This goes the other direction. It's called electrolysis of water. Right? So this presence of bubbles is an indicator that a reaction is occurring. Here's an indicator that a color change is involved. So in this case, we have hydrochloric acid being added to a solution of cobalt nitrate, and the solution turns blue. There's a chemical reaction that occurs to make that change happen. All right, so the color change is an indicator in this case. Here we're adding two clear liquids, solutions, homogeneous mixtures, adding them together, and a reaction has occurred which produces a solid. The solid in this case is yellow. And if we give it enough time, it will settle to the bottom. It will precipitate. The two solutions are sodium dichromate and lead nitrate. In this case, we're forming a solid. Now, many of these clues that we look at, the formation of a gas, formation of a solid, many of those clues are also indicators of the driving force for a reaction. Why does the reaction occur? If it produces a solid, then the solid is removed from the reaction and it pulls the reaction to one side. We'll talk more about that later. But formation of a gas is a similar way. We make these bubbles and one reactant becomes two products and they float to the surface and they're gone. They're removed from the reaction environment, which drives the reaction toward production of more gas. So think of these reactions in terms of what's driving the reaction also. Okay, here's an example. Methane, which is the principal component of natural gas, and oxygen being delivered in the air. So if you turn on your gas burner, if you have natural gas piped into your house and you need to turn the stove on and cook something, then you'll see this reaction. Methane combines with oxygen and it produces two new substances, carbon dioxide and water. So when we write the reaction, let's see, I think there's some more. Yeah. When we write the reaction, it comes in a standard format. And that format is reactants on the left, separated by an arrow, and products on the right. This means that the reaction is proceeding from left to right. That's the indication. And then when we write the reactants over here, we put one reactant here, which is methane, and it's being added to another reactant to produce products. It produces two products, right? And we've learned how to write these formulas, elements, this diatomic element, and these compounds. We know how to write them. We know how to name them. This one has a special name, is methane. You haven't learned how to name those yet. and may not, depending on how far you go in chemistry. But that's why we're telling you what it is. This is an element, diatomic element oxygen. This is the compound. Remember, a type 3 compound, two nonmetals, carbon dioxide. and this is water. It's dihydrogen monoxide, but it has a special name. That's water. Okay, that's the format. Now notice one other thing about this equation. And think of this in historical terms. When the law of conservation of mass was proposed by Lavoisier in the late 1700s. Yep. He said that the total mass of all the reactants is equal to the total mass of all the products. Okay. Then when we came to John Dalton, Dalton said that the reason for that is because you have the same number of atoms on the reactant side of each element as you do on the product side. That's why the masses are equal. So that means if we have one carbon over here, we need one carbon over there. If we have 4 hydrogens over here, we need 4 hydrogens over here. We don't have that. So what that means is this equation is not balanced. Now we're going to learn how to balance equations in just a few minutes. But that illustrates the point that this equation as written does not obey the law of conservation of mass. All right, there it is in black and white. That's how you write a chemical equation. We also know that during a chemical reaction, atoms are not created and not destroyed. That's also required for the conservation of mass. Yeah, I was trying to move something here and it won't move. There it goes. Okay. So this is what I just told you. The same number of each type of atom on both sides of the arrow must be present in order for the reaction to be balanced. Sometimes we have reactions that are composed of polyatomic ions, and we discussed those in the last, it might have been a couple of chapters ago. Sometimes those polyatomic ions remain intact from one side to the other, which is useful. And I'll show you why that is in just a few minutes. So here's our unbalanced equation, and we know it's unbalanced because we counted up the number of atoms of each element and compared them on either side. And we find that it's not balanced. So in order for the equation to be balanced, we need a way to balance it without breaking any laws, any rules, right? And the first rule is, once the compound is written, you cannot change the subscripts. They're chiseled in stone. They remain constant as written. So the only way you can change the numbers is to introduce another factor, which we call the coefficient. We put a number in front of the compound, which means if we have H2O, this means there's only one water molecule here. If we put a 2 in front of it, that means there are 2 water molecules. It also means that there are 2 times 2 or 4 hydrogen atoms. And 1 times 2 are 2 oxygen atoms. Right? So when I did that, I gave us 4 hydrogens and 4 hydrogens. But I also gave us 2 oxygens and here 2 oxygens, so we have 4 oxygens. So now we need 4 oxygens on this side. If I put a 2 there, that gives me 4 oxygens. Now that should be balanced, and it should agree with this slide, and it does. Now that was what most textbooks in chemistry call balancing by inspection, right? But I'm going to give you a method for balancing equations that is reliable, more logical, and more efficient in use of your time. But first, we need some more information that can be delivered by an equation. In this case, notice that we have symbols here, an S, an L, a G, and an AQ. Each one has a meaning, right? Solid, liquid, gas, or aqueous solution. In this case, methane is a gas. So we follow it with a G in parentheses. That means it's a gas. Oxygen is also a gas. Carbon dioxide is a gas. And this reaction produces a lot of heat. So at the temperature of the reaction, water would be a gas. It would be a vapor. But if we wrote the equation and we wanted to assess reactants and products at room temperature and pressure, then water would be a liquid. Right? So that also helps you understand something about the equation and the conditions under which the equation is evaluated. All right. So in this particular equation, we have a reactant, which is a metal. Potassium, solid, right? You know K is potassium because you memorized the symbols. And then if we put potassium in water, which is a liquid, it does a couple of things. It produces a gas, hydrogen gas, as a product. And it also produces an aqueous solution. An aqueous solution of potassium hydroxide. Hydroxide is a polyatomic ion. So we name it potassium hydroxide. All right. Now, I'm not saying this may or may not be balanced. I haven't checked it yet. But if you look at the evidence, this potassium metal here is submerged in mineral oil for good reason, because potassium is an extremely reactive element. It will react with either water in the atmosphere or oxygen in the atmosphere, and probably both. So we keep it from reacting by submerging it in mineral oil, in which it will not react. Now, water is in the middle, and on the right, you have the solution of potassium hydroxide, and you also have the bubbles forming, and there's a lot of heat produced. So when this hydrogen is evolved as the gas, and it reaches the surface of the liquid, it mixes with oxygen in the air. So now you have this gas becoming another reactant and mixing with oxygen in the air. And that's my symbol. That's the symbol for heat. Heat is being added because this reaction produces a lot of excess heat. And there's enough heat there to cause this reaction to proceed. And it makes water vapor. Now, that's not balanced either, but it does tell us something about the reaction and why you see a flame there. The flame is actually a separate reaction. All right. So let's take this problem and see if we can make sense of it in terms of chemical reaction. Okay, when blue light shines on a mixture of hydrogen and chlorine, right? Sometimes it's valuable to draw a picture. So let's say we have a container here, and it's sealed off with a stopper. And inside we have hydrogen gas and chlorine gas. Notice that I wrote a 2 here on each one because they're both diatomic elements. Those I had you memorize. When we shine blue light on it, okay, this is blue light, which is a higher energy form of light than red light. What is happening? Well, you get a violent reaction, and they produce a gaseous substance called hydrogen chloride. Right? That yields HCl gas. Now, if we wrote that out like we were practicing earlier, we would write this like this: hydrogen gas plus chlorine gas yields hydrogen chloride gas. Okay? That's the unbalanced equation right there. How do we know it's unbalanced? Because there are 2 hydrogens here, there's only 1 hydrogen there. And there are 2 chlorines here and only 1 chlorine there. So we know it's unbalanced. Now we're going to learn how to balance equations. The atoms of each element on the reactant side must be equal to the number of atoms of each element on the product side. That's a fundamental requirement of a balanced equation. Because we cannot create and we cannot destroy atoms in a chemical reaction. Most of the time, when you're asked to balance an equation, you'll be given the reactants and the products. Now, you may not be given them in this form, right? As elements or compounds written in there with their symbols. You may be given their names, right? So that's why you had to learn how to write compounds from the names. But usually they will be given to you. There are a couple of situations where you can deduce the products. And if it's appropriate, I'll mention those later. Otherwise, you'll be given the reactants and products, at least in their names, and then you write the compounds to generate the equation. The formulas, once the formulas have been written in this format, you cannot change them. Right? If you change the subscript of a compound in order to balance an equation, then you're cheating. Right? And you're not just cheating, you're breaking chemical laws in the process. All right. So the first thing you do is read the description of the chemical reaction. Right? It'll be given to you in some format. What are the reactants? What are the products? And what are their states? Now, sometimes the states are not important, and we may omit them, but many times they are essential to understanding the chemical reaction. So be aware that they may be given to you and need to be included. So we write the proper formulas from their names, if that's required. Right? Examples. Then you write the unbalanced equation. You put those chemical formulas in their places as reactants or products. All right. Then you balance the equation. The creators of this slide said balance by inspection, but I'm saying that's cheap. That's what we used to call a cop-out. When you tell a student to balance an equation by inspection, you're not telling them much, right? You need to give the student more information, a method for balancing. So I'm going to do that in just a minute. This will be one way of inspection. It takes up a lot of room and it's messy. All right. I'm not going to dwell on this equation because we've already done it. Plus, I want to get to the method and show you how to balance equations. But once you've balanced the equation, you check to see if, in fact, the rules have been obeyed. The same number of atoms of elements on this side and that side. And the method I'm going to show you allows you to assess that instantly. I will make this point, though. Technically, the equation, this particular example of equation, is balanced in either the upper equation or the lower equation. But notice that the lower equation could be simplified, right? If we had, let's say we had this one here, here, and here. Instead of that example, let's use this example. This has 4 hydrogens. This has 4 hydrogens. This has 4 chlorines. 4 times 1. This has 4 chlorines. So technically it's balanced. But by convention, we balance equations with the simplest whole number ratio. Now the ratio is established, right? This ratio is established at 4 here, 4 here, 4 here, 4 here. The question is, can we divide the entire equation through by a single number divisor and reduce the values of these? And the answer is yes. We just divide the whole equation through by 2, right? This is math. 2 divided by 2 is 1. 2 divided by 2 is 1. 4 divided by 2 is 2. So that is the simplest whole number ratio. A 1, remember, there's always a 1 here. If you've got a compound or an element there and there's no number, it's always 1. We just don't write it. If you got the symbol, it has to be at least 1. Otherwise, you wouldn't write it there, correct? So that's 1, that's a 1, that's a 2. That's the simplest whole number ratio for this equation. And that's what we prefer. All right. Okay, these are helpful hints. And you'll find these reproduced in, let's see, where is that document? Here. You'll find these slides reproduced on this document that you'll find in Brightspace. I just put them in here so they would be recorded and available in this format. But what we're going to do is we're going to use these helpful hints in examples. Right, so right now they're just listed. The first helpful hint is if your equation has a single element on one side or the other of the equation, save that one for last. It's very simple. because as we're balancing the equation, if we put a coefficient in front of the element, it only changes that element. Right? If you try to balance a compound last, you're going to be changing two or more elements, and then you have to go back through the equation and look for other places where that element occurs and balance again. So we hold elements till last. Okay. As a general rule, we hold water to last too, if we can. Next to last, excuse me. Hold elements to last, water next to last. Many reactions incorporate water, and it only has two elements in it. So it's a good practice to hold that one if we can. Sometimes, as an intermediate step, we introduce a fractional coefficient. So in this case, we see we need 25 oxygen atoms. Only our element is diatomic. If we need 25 of those, then 25 halves will give you 25 oxygen atoms, right? It's math, right? This is 2, that's a half. So we take a half of the oxygen. Oxygen's like this. If we take a half of an oxygen, we have this much. So we have a half of an oxygen and 25 of them. So that's 25 oxygens. These are helpful hints. I'm just giving them to you now. We're going to use them in a few minutes. Here's another possibility. Suppose you need to, let's see. Yeah. If an element occurs on both sides of an equation, and the subscripts of the element are odd and even. In this case, we're looking at, let's see, hydrogen, I think. On the right-hand side, we have water with a subscript of 2. And on the left-hand side, we have ammonia, NH3, ammonia with a subscript of 3. Well, if we're trying to balance the hydrogens, you can't multiply one side only and come out with a value that equals the other side, because they're odds and evens. So one of the tricks that we can use is we use two coefficients at the same time. But in order to do it, we take, see, if you have ammonia on this side, I'm only going to use the ammonia and the water part. Right? So we have a 2 here and a 3 there. If we take that 2 and put it over here, take this 3 and put it over here, then we have 6 hydrogens and 6 hydrogens. Okay? And in math, that's called cross multiplication. All right. So, this one also includes, this example includes another helpful hint. If you have polyatomic ions in your compounds, and the polyatomic ion remains intact on both sides of the equation, then we can use it as a balancing group. And I'll show you, we'll go through this example. I'd rather do one, that was a little complicated. Let me see, let's try one. In fact, let's take a look at that one we just did. Let's see, ammonia, oxygen, NO, and H2O. Yeah, that was a little complicated too. Let's try, okay. Let's try this one. instead of methane, let's try C2H6. So it's another organic compound. It's a hydrocarbon called ethane. And we're going to burn it, right? And it's going to produce carbon dioxide and water. Okay, we know that. These two together will burn to produce those products. So you're given the reactants and the products. Now, the way we set this up is my budget method. So we put the elements down this side. We've got a carbon, we've got hydrogen, we've got oxygen. That covers all the elements in the equation. And then we do an initial inventory. How many carbons do you have on this side? We have 2. How many hydrogens? You have 6. How many oxygens? You have 2. And on this side, we have 1 carbon. We have 2 hydrogens. And we have 3 oxygens. Okay, that's your initial inventory. And very often I like to check myself to see if I miscounted. So we have 2 plus 6 is 8, 9, 10. So this is 2 and 4. 2 plus 2 is 4 and 6 is 10. So that's a good count. And we do the same thing for both sides. Now, the next thing you ask yourself is, where do I start? Well, we know we don't start with oxygen because we want to hold that one to last, right? Okay. And water would be second to the last. So let's start with carbon. We need 2 carbons on that side, so we put a coefficient right here. That's 2 carbons. It also changes the oxygen. Now we have 4 oxygens plus 1 is 5. 5 oxygen. All right. Notice as we proceed, we can see instantly 2 and 2 carbons are balanced. Hydrogen 6 and 2, they're not balanced. Oxygens 2 and 5, they're not balanced. So next we go to hydrogens, because we're still going to hold oxygens till last. We need 6 hydrogens on that side. Hydrogen occurs in one place. So if we put a 3 here, that's 2 times 3 is 6. But that also gives us 3 oxygens plus 4 is 7. Okay. Now we've got carbon and hydrogen balanced. We need to balance the oxygen. We're going to use the fraction trick. We need 7 oxygens on this side. But there's no way to multiply. If we use 3, that's only 6. If we use 4, that's 8. It's too many or too few. So we use a fraction. So we use 7 halves times this one, right? This is 2 times 7 halves gives you 7 oxygens. Now it's technically balanced, but we don't like fractions. So we're going to get rid of the fraction. How do you get rid of a fraction? First of all, the ratios are established now. This is balanced. 1 to 7 halves to 2 to 3. That ratio is fixed now. But if we multiply both sides by the same value, then we have not changed the ratio. All right, we're using some of the rules from math. So how do we get rid of that half? We multiply the whole equation through by 2. So 2 times 7 halves, right? 2 times 7 halves is equal to 7, correct? All right. So 2 times 1 is 2. 2 times 7 halves is 7. 2 times 2 is 4. And 2 times 3 is 6. Okay. And we've used up that 2. Right? It was balanced before. It's still balanced. So our coefficients are 2, 7, 4, and 6. Right? Now we have a balanced equation using the budget method. Okay. So now let's go to the one with polyatomic ions. All right. There's our polyatomic ion. And I've set up this table to show you that if you have polyatomic ion on both sides of the equation that's unchanged, ammonia, for instance, NH4, is the same on both sides. We're going to use it as a balancing group. That greatly simplifies the process if you don't have to break everything up into individual atoms. Phosphate is also a polyatomic ion, same on both sides. Notice there's an error here. That 4 should be a subscript. And the other elements we have are calcium and chlorine. So now we're going to do our inventory. We have 3 ammonias. We have, on the reactant side, we have 3 ammonias, 1 phosphate, 1 calcium, and 2 chlorines. Then on the product side, we have 1 ammonia. We have 2 phosphates. We have 3 calciums. And we have 1 chlorine. Right? So we can see that it's not balanced yet. So the question is where to start. We don't have any elements off by themselves, so there's nothing to hold in reserve. There's no water there, we can't hold that in reserve. So in this case, it requires a little bit of intuition, practice. If you practice a lot of equations, balancing equations, then you're going to see at a glance which one would get you there quicker. Now, we could start anywhere, and we would end up with a balanced equation. But it may take more steps one way than the other. In this case, I want to start with calcium. So in order to balance the calciums, I need a 3 on the reactant side. Right? Now we re-inventory. Right? That first step, that little red 1 tells you this is the first step. So we're going to have 3 calciums on that side. We're also going to change the chlorines to 6. Okay? Now what's next? Well, we got the calciums done. What if we balance the chlorines? All right. Well, no, it looks like I'm doing something else. No, oh, that's right. Yeah, we're going to balance the chlorines. I need 6 chlorines on the product side. So that 6 changes the ammonias to 2. To 6, pardon me. 6 ammonias and 6 chlorines. Okay. So now we've got the calcium and the chlorines balanced. Right? During the balancing of an equation, sometimes you have to change several times. But at this point, calcium and chlorine are balanced. We've got ammonia 6 on the product, on the reactant side, the product side. Now we need to change the reactant side. That's our third step. Put a 2 in front of that ammonia. Since ammonia has a subscript of 3 times 2, that's 6 ammonia groups. Okay, but we've also changed the phosphates. So we got to re-inventory the phosphates. And we're balanced. I think I'm going to fill in the rest of it just to be, 2 there and 3 there. So you can see at a glance, now the equation is balanced. All right. Balance the following equation to the lowest ratio of whole number coefficients. and then determine the sum. So we've got this compound plus oxygen. Let's see. Yeah, we put the phase there. And it's going to produce this product. All right. Let's name these. Well, that's oxygen. How about this one? Well, oxygen is 2 minus. That means this has to be 2 plus. This is iron 2 oxide. All right. Again, 2 minus, minus 6 here. We need a plus 6 total. This is plus 3. This is iron 3 oxide. Both of these compounds are type 2. They're metal, non-metal, and the metal has a variable charge. So on this side, the charge is 2 plus. On this side, the charge is 3 plus. All right. Let's balance the equation now. All right, let's do our inventory. Iron and oxygen. That's it. We got 1 iron and 3 oxygens here. We have 2 irons and 3 oxygens there. All right. So this is an easy choice. We can't balance. We hold the oxygen out last, of course, but that's a no-brainer because there are 3 on both sides. So we're going to balance the irons. So if we put a 2 here, that makes 2 irons, but 2 plus 2 is 4. Right? That makes 4 oxygens on that side. All right. So now, how do we balance that? Well, if we only need 3 oxygens, we've got 2 here. We only need 1 there, right? Wouldn't that be right? If we've got 2 oxygens here and 2 there, that makes 4. If we got 2 here, but there are only 3 here, why don't we just take a half of that one? Right? A half of that would be 1 plus 2 is 3. So we went backwards. Now we get rid of that fraction. Right? And we know we do that by multiplying by the denominator of this fraction. Right? So 2 times 2 is 4. And 2 times that is 1. Right? So we got a 1 there. And 2 times that one. Right? So the sum of our coefficients is 4 plus 1 is 5 plus 2 is 7. Okay? It just takes practice. The more of them you do, the easier they get. All right. Which of the following, okay, there must be some examples here. Which of the following correctly balances the chemical equation given below? There may be more than one correct balanced equation. Okay, so let's do this one. Calcium oxide plus carbon yields calcium carbide plus carbon dioxide. Okay, so we'll do our inventory. We've got calcium, oxygen, and carbon. 1, 1, and 1 on this side. 1 calcium, oxygen, 2, and carbon, 3. Okay, we're going to hold carbon to last if we can. And we're going to go for oxygen first. So we got 2 oxygens over there. We need 2 over here. Okay. That also changes the calcium to 2. All right. So now on this side, we need 2 calciums. All right, that changes 2 calciums That gives us 5 carbons. And we still have 2 oxygens. Okay? Let's see if that's right. So 4, 5, 1, 2, 3, 4, 5. Yep. And this is 2 plus 4 is 6, 7, 8, 9. 5, 6, 7, 8, 9. Okay. Now we need to balance the carbons. We need 5 carbons on this side. Okay? And you can see it's balanced. 2, 2, 5. Now that's the simplest whole number ratio, right? 2, 5, 2, and 1. But if we multiplied those by either a whole number or a fraction, we could get this one if we divided by 2, or this one if we multiplied by 2. But the first one was preferred. That one's preferred. Simplest whole number ratio. All right. When balancing a chemical equation, which of the following statements is false? Okay, let's see. Subscripts in the reactants must be conserved in the products. No. We write the reactants and products separately before we even put them in the equation. Right? So A is false. How about B? Coefficients are used to balance the atoms on both sides. Yes. We use coefficients only to balance an equation. When one coefficient is doubled, the rest of the coefficients in the balanced equation must also be doubled. Yes. Right? Once the ratio is established in a balanced equation, whatever you do to one, you have to do to the others in order to maintain that ratio. So this one is also true. D, phases are often shown for each compound, but are not critical to balancing the equation. Usually, they're not critical. That's true. There are rare occasions where you do need to know the phase, because you may have a compound in one phase and a compound in a different phase being expressed in the reaction. But most of the time, the phases are irrelevant to balancing the equation. All right, so that was the false one in this group. All right. The number of atoms of each type of element must be the same on both sides of the balanced equation. Yes. Subscripts must not be changed to balance an equation. True. A balanced equation tells us the ratio of the numbers of molecules which react and are produced in a chemical reaction. That the coefficient ratios tell us how much of each reactant and product are required in order for the reaction to obey the law of conservation of mass, among other laws. Coefficients can be fractions, although they're not usually given as the lowest whole number integers. Ratios are better. Now, there are situations where we have to use fractions, right? But if you use a fraction, that changes the interpretation of the equation. Because with whole numbers, we're saying, right, that's one molecule of water. Okay? But if we say this, how can we make a half a molecule of water? You can't. So there's another interpretation that we'll get to. I think it comes in chapter 7. Let me just check for a moment. Actually, I can discuss it now. In the chemical equation, we can interpret it as this. With 2 here and a 2 there. We can say 2 molecules of diatomic hydrogen plus 1 molecule of diatomic oxygen yields 2 molecules of water. Or remember the concept of the mole. We can also say 2 moles, or 2 times 6.022 times 10 to the 23rd molecules of hydrogen, 2 moles, plus 1 mole of oxygen yields 2 moles of water. When we say that, now we can say that yields that. Right? We can just cut them in half. Now 1 mole of hydrogen molecules plus a half a mole, a half of 6.022 times 10 to the 23rd, yields 1 mole of water. Then we can do fractions, physically speaking. Right? If we're just talking about atoms and molecules, we actually can't take fractions of those. Right? We'll talk about that more later. Just remember the preferred way is simplest whole number ratio. Now, let's see. Yeah. This is the last slide in the group, and we're just going to introduce this concept, and we're going to work it out in more detail later. But the advantage to having a balanced equation, which is a complete sentence, words plus words yields words. Having a complete sentence, a balanced equation, allows us to track the progress of a reaction in terms of what goes in must come out. Okay. That conserves mass. So we know that we can calculate the mass of reactants and we can predict the mass of products. That's called stoichiometry. But the first thing you do, actually, first thing is you're given the reactants and usually the products, then you write their correct formulas and you put them in the equation and you balance the equation. And from the balanced equation, then we can move to actually identifying how much of reactants and products are present in a reaction. That's stoichiometry. And that's the end of chapter 6. Okay. I see. Since there's nobody here to ask questions, we're done for the day.